9th. We are talking about imbalanced data sets today in CS 746. I guess we'll just go ahead and get started here and see how fast we can get through this, because in the other class, how many people in this class are in ADS? One. Are you planning to take the tour? Okay, so you'll have to leave early to get over there by 11:50, something like that. We have the other group, the other class is taking a tour of NetApp building, but they gave us a tour at 12 o'clock, which is in the middle of this class. So I'm going to try to get this done. It's a short-ish lecture, so we'll get done soon enough. Okay, so course outline. We are actually on the very last thing in our course outline. Yay, imbalanced data sets. So remember, we talked about credit card fraud detection data set. And that was an example of, classifying the data into safe and fraudulent uses of the credit card, right? And we ran those chosen classifiers. We got accuracy scores, naive Bayes, and logistic regression of 0.993 and 0.998, which sounds pretty good. But when you start looking at the details, you might see that there's a little problem, though. It's an imbalanced data problem because we got, 99.8% of our samples are non-fraudulent. So if we just measure the accuracy, right, there's a large discrepancy. Most machine learning algorithms we've talked about so far were designed around the assumption of an approximately equal number of examples for each class. And so a lot of models, when you get into minority classes, they have very poor predictive performance. So why does this happen? Well, basically, they're all designed to look for the of accuracy, right? Try to minimize the errors. So looking for true positive plus true negative over the total set. They're trying to get that percentage as high as possible. In the fraud data set we just looked at, if we predicted always that there was no fraud, we'd be 99.898% accurate, which is great in the sound of it, right? Except it didn't detect any fraud at all. So anytime there is an imbalance in data, the larger the imbalance, the bigger the issue, right? But if you have just twice as much of one class of data as the other, you're still getting just an imbalanced data set where, you need to pay attention and make sure that you're not having problems with your analysis because of that, right? And when you get into very heavily skewed stuff, then your big problem gets even bigger. So what we're going to do is we're going to change the metric. And we've already seen this slide in kind of different shapes and sizes, but we're going to look at precision and recall. Where precision is the true positive over the true positive plus the false positive. In other words, how precisely did we pick out the positives? And the recall is how good were we at finding the ones that were labeled by the experts. So here again, our test predicts it's true. How many of the things that it predicts is true are actually true? That's precision. How precisely did it hit the target? And recall is how well did it find the ones that we know are true, right? So how many times did we miss something that was labeled and we said it's not true, right? And the F1 score is, of course, a weighted average of those. We take the 1 over P precision, 1 over the recall, and we're going to build the area under the curve where we're going to actually, instead of measuring the recall, we're going to do something a little bit opposite the recall. We're going to measure the false positive rate. So we get false positive over true positive plus false negative. This is basically 1 minus the recall here. And that'll be our area under the curve, under the receiver operating characteristic curve. And so the goal is, if we just pick a random observation from each class, what's the probability that our model will be able to rank them correctly as being in the true or the false class, right? Okay. So if we have a dummy classifier, it says no fraud in every case. We can see that for case 0, our precision is 1, our recall is 1, our F score is 1. We can see for case 1, where we know our actual is down here. If we predict 0, we get a precision recall F1 score of 0, right? So for each of those, we have a very poor on the minority case, right? Our accuracy is 99.8%, but our area under the curve is only 5% or 50%. So that's flipping a coin, right? If we try the naive Bayes classifier, in this case, we get very high precision recall and F1 score for the majority case. We do get some correctly classified minority cases, but you can see we actually pick up some false positives and false negatives, right? So our precision is only 14%. Our recall on the minority case is 66%. Our F1 score is only 23% or 0.23. So that's not so great, right? We look at our logistic regression. Similarly, we see, for the majority case, it's great. For the minority case, well, we're doing better than naive Bayes and our precision, right? We're not misclassifying things quite so much on this case. A lot fewer of these false positives there, right? But it still could be better. We've only got an F1 score of 65% or 0.65 here, right? Area under the curve is 0.1. Our area under the curve here was actually higher with naive Bayes, even though we had more misses on the minority case, right? So what we're looking for is, can we do better than those, right? Well, how can we do better? There are 3 different techniques. One is collect more data. Get some more of those minority cases, right? Another way to do it is what's called sampling method. We can oversample the minority case, or we can undersample the majority case. Those involve either creating data out of thin air or throwing away useful data we've collected, right? And finally, we can use different, more robust models. And if this looks like a decision tree and maybe a piece of a random forest, that might give you a hint as to what a more robust model looks like. So sampling methods, undersampling, we just take thin slices of our majority case and only use those. So we end up with approximately equal sizes. Or we take our minority class and we just make copies of it, right? Until we have as many instances of that data as we have of the majority case. Now, we don't want to just do this naively. We don't want to just copy the data, right? So let's look at some of the most popular ways to do it. So Tomek link is we take pairs of observations that are very close to each other, but are in opposite classes. And then we remove the majority case of each pair. And basically what we do is by removing the blue circle from all these pairs, we end up with a sharper boundary, right? We don't have any of the majority cases stuck in the middle of a minority case. We're going to go ahead and accept, possibly an error if we see that particular case, right? But the point is that we want to make our classification of the minority case be as good as the classification of the majority case, right? So this basically sharpens up the border, puts a little space in there, and allows us to classify more clearly, right? From imbalanced learn.undersampling, import Tomek links, and away you go on that. Some other undersampling methods besides Tomek. Near miss 1, select only those majority class examples that have a minimum distance to 3 minority class instances. So basically what we're saying is if we've got a data point like this one down here, it's in the majority class, but it's buried in a minority case, we're going to throw that one away because its 3 closest neighbors, right, are in the minority class, right? So that's just going to mess up our analysis if we leave that data point in there. Condensed nearest neighbor rules, right? So we enumerate all the examples in the data set. And this is where we're trying to be better at doing our actual data prediction, right? So we add them to our data set only if they cannot be classified correctly by using the current contents of what's in our store. So we're building up, we're calling our useful data set, right? And so if we see something that is a majority case, it's way the heck over here. There's no way that we're going to make an error right? We're not going to bother putting that into that. So what this is trying to do is undersampling by preserving things close to the boundary, right? Edited nearest neighbors rule. We're using three nearest neighbors, or another similar number. Locate those examples that are misclassified in the majority set, in the majority class, and then we remove those before we do a k=1 classification rule. One-sided selection combines the Tomac links and the condensed nearest neighbors rule. And the neighborhood cleaning rule, and this is, I call this the nosy neighbor, homeowners association rule, right? You combine the condensed nearest neighbors with the edited nearest neighbors. So you remove redundant examples here, and we remove noisy or ambiguous examples down here. In this case, we are looking for not so much improving the balance of the class distribution. We're looking for the quality or the lack of unambiguity, the information content of the examples that we do retain in the majority class. So this is things that are unambiguous, that don't cause problems with the minority class classification. Okay. Pros of undersampling: it's easy to implement. Training becomes more efficient because when you throw away data, you have less data to run your model on, so your model can build quicker, right? For some domains, it works very well. Unfortunately, the fact is you are throwing away a lot of data and a lot of information that could potentially be useful. So you want to be careful not to throw away stuff that you really needed to keep, right? So let's try oversampling. SMOTE. Synthetic minority oversampling technique. I was going to chuckle at this. I used to work with a guy whose name was Smoot. And so, yeah. It was a synthetically oversampled ordinary something. I don't know what that stood for, but it sure was close to SMOTE, right? So we generate synthetic data for the minority class. So what we do is we randomly pick a point from a minority class, compute the k nearest neighbors for this point, and then we add synthetic samples between that chosen point and its k nearest neighbors. So we'll come out here, we'll take these classes, we'll go in here, we'll say we'll add things, a point that's closest to these 3 points, we'll add a synthetic point, at the intersection where these 3 neighbors are closest. And here we've got 4 for some reason. Here we got 4, right? Yeah, okay, this is doing k. Yeah, we're doing 4 neighbors. I'm sorry, because it's a 4 neighbor rule. So we're finding, for each sets of these 4 points in a minority class, we're just going to go ahead and try to fill in a synthetic point in the middle there, right? So we're not cloning the data. We're actually creating new data out of thin air, right? But, given if the type of the data set fits, then this can be a valid thing to do. So, and again, from imbalanced learn oversampling, import SMOTE, you can go with that, right? There are a couple different ways to do SMOTE. You can do borderline SMOTE, where you basically look in the minority class and find things that have been misclassified. And we use the k nearest neighbors classification model to do this. And then we oversample just at those instances. So basically what we're doing is we're kind of putting more minority points where things are accidentally labeled as part of the majority, right? So we're not putting points in at random amongst all the minority case. We're putting them only where we have need more information, right? Borderline SMOTE / SVM, we're using a support vector machine. In this case, we're going to try to select regions where there are fewer examples of the minority class, right? And then we extrapolate towards the support vector machine boundary between the 2 classes, right? So we're basically going down here, we're saying here's our boundary, we're trying to find ways to sharpen up that boundary using our support vector machine, right? Oversampling is, again, easy to implement, uses all of your training data. It tends to perform well in a broader set of circumstances than undersampling or subsampling. And it is, cons though, is in order to train your classifier, now you have to be able to create all these synthetic data points by some method, and that can take a lot of compute power to do that, right? So it's computationally expensive. We can do combinations, over and under sample, right? Goodness, I thought I had 32 slides. It says I only have 23. Cool. This is going to be a nice short lecture. I'll get to go on the tour, I guess. Okay. So under and over sampling techniques. So basically we can do smoke Tomek, right? So we're doing synthetic minority oversampling, and we're doing Tomek links to eliminate majority classes and add minority classes. And so this is kind of just getting more balanced by a balanced approach, right? And then smote versus edited nearest neighbors is another method to do that. Right? There are other ways to deal with unbalanced data. And this can be more useful. We can change our approach. We can say, instead of using Tomek or instead of using smote, we're going to go out there and start doing anomaly detection, right? So we use methods, techniques that only train on a single class. Say, is it a member or not, right? Another way to do it is to make sure you do use the right metrics. Of course, we say here, never accuracy, right? And we talked about, the problem with misclassification. If you tell someone they don't have cancer when they do, it's more of a problem than making the opposite error. If you tell someone that email from their, credit card company is spam when it's not, that's another kind of error, right? So you want to be looking at, precision and recall and weighting those metrics appropriately for the situation you're working on, right? Or we can use more robust algorithms, or write your own algorithm. Come up with an algorithm that's kind of, basically, if you know enough about the data, you can maybe come up with a better algorithm than what's out there in the, standard toolbox, right? And so you can start modifying it, whether you're just changing hyperparameters or writing something brand new and getting your PhD in data science because you've done something that added to the knowledge of the, the practice, then great, right? So some of these more robust algorithms, one class classification, anomaly detection, gradient boosting classification. And we're doing a classification task where we're looking to find where things change. And we're looking for that gradient there, right? We haven't got into this algorithm very much in this class, but we did get into random forest. And of course, the cool thing about random forest is it takes not just, moderately well-performing decision trees and aggregates them together. It can also take moderately poor quality data, right? And can extrapolate by using multiple decision trees. It can actually go out there and do a pretty decent job of classifying both the majority and the minority cases. So here's an example. We're doing random forest versus logistic regression. Random forest on the left, logistic regression on the right. You can see logistic regression gives us an area under the curve of 0.801, 80%. Precision on the minority case is okay, right? But when we start plug this into a random forest, doing the magic of randomly sampling things multiple times in different ways, we end up with a precision 95%, recall 70, almost 80%, F1 score 0.86, area under the curve almost 90%. Right, so we can get a really strong model out of using that random forest. So, it's like kind of like I feel like we saved the best for last. We should just start the class with random forest, and so we're just going to do that and ignore all the rest of that stuff. But now you need to know all the tools, right? Okay, and of course our accuracy score is actually slightly worse with the random forest. Oh, no, it is better. That's 3 nines. Yeah, slightly better with the random forest, but we're not going to focus on that accuracy score because it's not a great metric. We want to look at the precision, the recall, the F1 score, and the area under the curve as our best metrics, right? So we also have some examples. Now, I'm not going to go into these. Instead, I'm going to run off and try to catch up with the tour over at NetApp here before it gets to be too late. That starts at 12 o'clock. So I'm going to call class off pretty early today. But if we start here, there's a couple of links here about how to use autoencoders. And so this is specifically using autoencoder for doing credit card fraud detection. And I'm just going to post this, of course, on the Blackboard. It's already up there. So you'll be able to find that. And I'm going to recommend at this point you go ahead and read this on your own time if you're interested in this. And there's a better, I mean, this is just full of wonderful memes, right? And looking at this and so on and so forth. And so another example of an autoencoder is from Google, their TensorFlow, artificial intelligence, of course. And they're going to give us an example of how to do autoencoders. And they talk about, they have some kind of more straightforward explanation. An autoencoder, you have your images, black and white, and it's reconstructing what it is. So it's being able to do classification, right? And so we got is two layers here. We've got an encoder which shrinks it down to a smaller data set, and then a decoder that reconstructs the original image from the latent space. So it actually can take this message, save space and storage, compress the message using the autoencoder, right? Another way that you can do with the autoencoder is if you've got, and you see it doesn't reconstruct perfectly, right? But if you got a lot of noise in your message, in your image or your message, right? Your autoencoder that can go ahead and take that and reconstruct the original, eliminating the noise from the message. Finally, it can use the anomaly detection example where we're looking for things that are not expected in the data, right? So this is another good resource to look at. And the nice thing about this one at Google, of course, is being Google, it's all up in Colab, and this code is, you can copy the code, you can put it, and it's literally in I think you have to log in order to get to it, in order to actually use it live, but it's actually got the code that you would have in your Google Colab in your Jupyter notebook, right? So that's kind of a useful stuff here to, and this is basically all part of understanding TensorFlow, doing artificial intelligence work at Google, and they have good training stuff that they put up from that company, right? So it is now literally 11:30. And I basically have managed to go through all the slides in short order. So let's go ahead and stop the recording.